Okay, this here is the talk about the Qt continuous integration system. I hope you're in the right room. So before we start, I'd like to introduce a concept to you. So within the world of software engineering, we often talk about releases. So for example, Nokia recently released Qt 4.7.0. There is also the concept of a brown paper bag release. Does anybody know what that is? Yep. One person, good. So basically, that is when you have released some software and it contains some bug that is so embarrassing, you want to put a brown paper bag over your head. So has anyone actually been involved in a release like that? Yep. Okay, a few people, good. I was a bit worried that no one would admit to that, but okay, that's good. So basically what I'm talking about today is, in a nutshell, the anti-brown paper bag system that we have in place at Nokia for Qt. All right, so this is what we're going to talk about today. First, I'm going to go through why do we have this continuous integration system, what's the background behind it. Then I'm going to talk about how it works. So that will be a little bit of high-level information and a little bit of implementation detail as well. And then I'll talk about the next steps. So notice that I have not yet attempted to define what continuous integration means. This is a term that is used a lot within the world of software quality assurance, and it means different things to different people. By the end of this talk, you'll understand what it means to us at Qt. Okay, so let's get right into the first section. Why do we need a continuous integration system? Well, I want to go right back to the very early days of Qt. So 1991, Qt 1 was released, and the very first development of Qt was done by two guys working out of their home, financed by their wives. Okay? So these guys were doing all quality assurance processes by themselves. All kinds of things like testing, release engineering, documentation. That was all done by the same people actually hacking away on Qt. Now, if we fast forward to today, we have Qt everywhere. Qt is on millions of devices, and we hope it will be on hundreds of millions, gazillions of devices. And when we have Qt with an install base of millions of devices around the world, it really doesn't cut it anymore to have developers developing code and then also being responsible for the QA for that code. So nowadays we have considerably more strict and formal QA processes in place. So a little more detail about the growth of Qt over the years. As I said, in the early days, it was just a handful of developers. By the time Qt 1.0 was released, there were 4 developers, 80,000 lines of code. Nowadays, we're looking at 3.1 million lines of code and approximately 200 developers. Unfortunately, that number of 200 has to be approximate. I couldn't find a way of getting precise numbers for that. But the exact numbers aren't too important. Basically, I want you to look at the pattern, and you can see that Qt has grown enormously, and it's just going to continue to grow, we think. So as well as Qt growing in terms of the amount of developers and the amount of code, it also has a lot more platforms nowadays than it used to. So this is actually a subset of the platforms that Qt works on. There's a lot of them. And many of these platforms have several configurations as well. So if you consider Qt on Windows, not only do we have to support Windows XP, Windows Vista, Windows 7, but there are 32-bit and 64-bit versions of Qt on those platforms. And there are different versions of Microsoft Visual Studio. And we also want to support MinGW, the GNU compiler on Windows. So as well as all these platforms, there's a lot of configurations that aren't represented here. Basically, the point I want to make here is that from the point of view of a Qt developer, it's a bit of a nightmare writing some code and making sure that it actually works on all of the Qt platforms that we offer. All right, so what conclusions can we draw from the data that I've shown so far? As I've just pointed out, there are many platforms. Unfortunately, that means that we have a lot more platform-specific code than we used to have. Okay, so in the early days, we had Qt for Windows and Qt for Unix, and that was it. Nowadays, we have Qt for so many platforms. What can easily happen is that a developer intends to write a small bug fix or a minor new feature. They think it's going to be a one-day job. Then they find out that they put it into the product and it breaks on some weird platform that they hadn't really considered. Fixing that bug might introduce a bug on another platform. And what happens is almost like a game of regression whack-a-mole with all the different platforms. On the other hand, we have more developers of Qt nowadays than we've ever had. So unfortunately, this means that the relative knowledge of Qt per developer is decreased. So to clarify what I mean by that, in the early days, when we had 80,000 lines of code, it was quite feasible for all the developers working on Qt to have some level of familiarity with all of it. Nowadays, that's just not practical. So, for example, we might have some developers working on QML who don't really understand about the implementation details of WebKit, and vice versa. So there's always a risk that these developers will make changes that may affect some other parts of Qt without realizing that. So when we put these together, if we don't do anything to handle this situation, Qt has a higher risk of regressions than ever before. So this is why we want to put some kind of system in place to help us catch these regressions. Okay, so we can outline some general goals for our continuous integration system. Now there's two ways of looking at this. There's, of course, what we would like to do, and then there's what we can do given the fact that computing power is limited and human resources are also limited. So ideally, we would come up with a system that would prevent any regressions in Qt from reaching any of our mainline branches. So by a mainline branch, I'm referring to Qt 4.6 or Qt 4.7 or Qt master, anything that might have a release made off of it at any point in time. The other important goal that we have is preventing regressions introduced by one developer from blocking the work of other developers. So in the ideal world, that's what we'd have. But we need to be pragmatic. That means that when we talk about preventing regressions, we have to limit ourselves to the regressions that we can actually test for quickly and reliably. And when we talk about regressions not blocking the work of other developers, well, let's just admit that if everyone is always breaking things, then the system might fall down a bit sometimes. Okay, so these are the goals that we were working with. So that's basically the background of the problem, why we found ourselves wanting to have some kind of a system in place to prevent these regressions. Now I'm going to go over what we actually have, how does it work. And we'll start with a very high-level overview. So I think this is pretty easy to understand. We basically have, at the top, we have some Qt development activity. This cloud here means that there could be anything in there. We're not defining what that is right now. Then at the bottom, we have Qt mainline, some Qt 4.7, for example, some branch of Qt that is supposed to be stable. And in between them, we have this thing called a quality gate. So what is a quality gate? Well, a quality gate can contain any kind of test procedure that's reliable and fast. So the basic kind of test procedure that we use for Qt is to compile Qt, run all of the automated tests for Qt, and compare the results with some baseline. Okay, so that's fairly simple, but the quality gate actually can contain any kind of tests. So also things such as checking the spelling in the documentation. If someone implements a test that does that quickly, then we can add that to the quality gate. All right, so we know what a quality gate is, but there's a very important question about this. What should this development part of the picture look like? remember, our goal is to enable regressions put in place by one developer to not block other developers. And that really shapes the solution that we're currently using, which is staging branches. So the basic idea with staging branches is that you take all of Qt development and you cut it up into a series of buckets. So these buckets or staging branches are usually mapped roughly to some team or functionality in Qt. So you can see there's a Qt WebKit staging branch and a Qt QML staging branch. Now the important thing to note here is that if some bug has been introduced in Qt QML, for example, it no longer compiles, that doesn't block anyone working on the other staging branches. Okay, so all staging branches feed into our mainline Qt here. Now, one thing that is important to note about the staging branches, so I put it on a slide on its own, this is something that people often misunderstand about the system when they're first introduced to it. We can't test our staging branches in parallel. The reason for that is that there can only be one candidate for a stable Qt version at any given time. So we can't preempt tests. If we're currently testing some staging branch, say Qt QML, let's say that fails, then the next staging branch can possibly be integrated. But in the other case, if we were testing Qt QML and Qt WebKit at the same time, and Qt QML were to pass, then Qt WebKit's test is invalidated because it was testing against the old Qt, not the new Qt. That might be a little difficult to understand, but hopefully this sequence diagram helps clear it up a little bit. So basically, this is what the system is doing in the case where it's successful. So on the left here, we have a staging branch, Qt QML 4.7, and on the right here we have our mainline branch, Qt 4.7. And in the middle, the process which drives it all, which I've referred to as the integrator. Okay? So the first step here is to fetch the latest version of the mainline Qt, so Qt 4.7. The second step is to fetch the staging repo. Then we attempt to merge them. Now, one thing that requires a little explanation here is this step 4, pushing back to the staging branch. So we want to ensure that developers are always working on top of a recent version of Qt, right? So what we do to enforce that is we always push latest Qt mainline, so Qt 4.7, for example, back into each of the staging branches. So that ensures that a developer is always working on top of a recent Qt 4.7 instead of, a month old. Okay, so it's important to note that this is allowed to fail, though, because there is a race condition here. If the staging branch has received more commits in the meantime, then our merge will be rejected. But that's okay. This is just a best effort thing. Okay, so the most important part of this process is that we actually do the test. So in this case, we've done a test and it's successful. And then we're going to push our tested version of Qt to the mainline repo. And then we tell people that their changes were integrated. We report the success. Okay, so that's hopefully the most common case, success. This is what happens when someone does introduce a bug. So the first 4 steps are exactly as you've already seen. But this time, we have a failing test. So that might be compilation fails, or it might be some auto test, which was previously passing, is now failing. When that happens, we do not push to mainline. We just report the failure. And for completeness, there is another case. There's the case of a merge conflict. So if there are developers working in different staging branches and they're working on closely related features, it can be that one staging branch is integrated into mainline, and then mainline now has a conflict with another staging branch. So in this case, we treat it similarly to a test failure, we report the merge conflict as a failure to the developers working in the staging branch, and they have to resolve it. All right, so with this concept of staging branches, the question naturally arises, what is the right amount of staging branches to have? Well, if we have a look, so I've drawn up a little table here that has a few different counts of staging branches and the results of having that amount. So if we assume that we can do a test of Qt, compiling Qt, and running all of the auto tests on all the platforms we're targeting, let's say we can do that in 2.5 hours, which is about the number that we have at the moment. So in this case, your worst case scenario as a developer is that you've written a patch and you pushed it to your staging branch, and after you've done that, you notice that the system just started to test your staging branch a few seconds before you did the push. So that's the worst case scenario. That means you have to wait for the current test to finish, and then you have to wait for a new test to start for your changes to be considered. So in that case, that's what I mean by maximum test time here. In that case, if we have one staging branch, we have a maximum test time of 5 hours. So that's not too bad. It means that if you do your changes in the morning, then you're guaranteed that you'll get a pass or failure report within the same working day. However, because we have 200 developers per branch, we are very likely to have overlapping breakages. So different developers introducing different regressions. By the time you fixed one, someone else has already introduced another one. The whole system is bogged down. So it's worth mentioning that having one staging branch, it's almost like the situation you have if you don't have any regression testing at all. Everything is going on in the same branch, and things are breaking all the time. So at the other end of the spectrum, let's say that we could have unlimited staging branches. So basically this means, well, all kinds of Git repository tools, such as Gitorious and GitHub, they usually allow you to create private Git repositories and branches. So let's imagine that we could use that, and we could set our system to look at any Git repository and branch that you ask it to. Well, that would be great in terms of developers per branch. There would only be one. And in theory, there would be no overlapping breakages at all if developers only put one type of feature in each of their private branches. But of course, the downside to this is that we have no idea how long it's going to take in the worst case scenario for your changes to be tested. Okay, so what I've highlighted here is 7 branches. I've highlighted that because that's what we've currently settled on as a compromise. So that's our current configuration, and in practice it works out all right. Most of the time you will get a test report in the same working day that you have submitted some changes for test. We do sometimes have overlapping breakages though. Okay, so I want to talk a bit about how we actually run these tests. So we use a commercial continuous integration server called Pulse. You may have heard of systems such as Hudson or Cruise Control or BuildBot. This is a similar system to those. Basically, the way it works is that we have a central server here, and we have some agents or test machines. We have about 200 of those. So we use Pulse in preference to the other products because it's very flexible and it allows us to implement whatever kind of workflow we want. Okay, so Pulse is a commercial product, like I said, and it has a web UI, and that's what it looks like. Sorry that's so small, but there is a lot of information there because we're testing so many platforms. There's not really that much to say about that. Another part of the test infrastructure is test results. Okay, so after we've done some testing of Qt, we need to put the test results somewhere where developers can view them. To do this, we have an internal web app built using Ruby on Rails. The only reason we have this is because there didn't appear to be anything out there that really did what we wanted out of the box. But there's not much to say about this either. It's a pretty simple concept. Okay, of course, we also have lots and lots of test scripts. So we have test scripts to do everything from compiling, running our auto tests, managing our artifacts. So by artifacts, I just mean some product produced as a part of the build process. So that's test results, build logs, binary packages. So we need to write scripts to copy these around, upload them to web servers, and so forth. And we also have a lot of code dealing with error detection and recovery. So by that, I can give an example to clarify what I mean. So when we're testing for Fremantle, MAMO 5, what can happen is that when we're doing an environmental update, so an apt-get update to update the newest packages from the MAMO 5 Debian repositories, it might happen that the repository server is having a few issues and it might time out, for instance. When this happens, it's not related to the code we're testing, so it doesn't really make sense to fail the test just because some server was having a bad day. So we actually have a lot of code in place that understands certain errors of this class, and it understands how to report the error and then continue the test. So our test scripts are written in a variety of languages. Perl is the most common. The reason for that is because Perl is already a prerequisite for building Qt from Git on all platforms. So we know that Perl exists on all the platforms where Qt is supported, and it works well, and also I just like Perl. But we also have things written in Python, Ruby, and some C++ Qt applications. And one of the goals here is to try to be equally cross-platform as Qt. So we have the same test scripts, understands how to compile Qt and run the auto tests on Windows as on Linux and Mac. Okay, so another part of the picture is, of course, the machines that we are doing these tests on. Okay, so basically we have 50 VMware ESX servers. I don't know the exact specs of them, but suffice to say they're quite powerful. And on these, we currently have about 250 Linux and Windows virtual machines running. These are not fully not fully utilized yet. So these test machines are very nice. The usage of VMware makes them very easy to manage. So VMware has a lot of programmatic, a lot of APIs where you can script the management of virtual machines, and we do make use of those to automatically reboot machines, move them around, run commands on all machines, all that kind of management stuff. So that's very nice. What's not quite as nice is our Apple machines for testing. So we've not yet found a feasible virtualization solution that's good in terms of performance and cost. So right now, we just have some Apple Xserves. They're running tests, and we don't really have a nice way to manage them in ways that are nice for test machines. So we don't have a way to roll them back to a good, clean state, for example. Our other different kind of Unix testing is a bit of a mixed bag. So in some cases, we are able to have virtualized Unix machines as well. So for example, we do test on Solaris, and that has the concept of zones. So that is like a container mechanism. And that does provide us with some nice capabilities, such as programmatically rebooting these machines without disturbing other tests running on the same hardware. And finally, I just want to point out that all these test machines do take quite a bit of effort to manage. We're using an open source tool called Puppet for this. So if there's any system administrators in the audience, you might have heard of this tool or similar tools such as CF Engine. So that's a nice little tool. Unfortunately, we're only using it to manage some of the test machines at the moment because it's not well supported on Windows yet. Okay, so let's move on to the kind of reports that's actually generated by the system. That might be a bit small for the people at the back. I'm sorry about that. These are reports, emails sent out by the system. They're real emails. The only difference is that I put in fake names because I didn't want to pick on anyone for causing build breakages. So this is what the system will give to you if you have made some commits to Qt, and they're all good. You'll get an email sent to you and sent to a mailing list. It'll tell you there was a successful integration of your staging branch. It'll give you a link that has some more details. I'll go into a bit of detail about what this blacklisted regressions were ignored means. And here's the list of changes that were integrated. Okay, so that's what it looks like when everything is good. Now let's say something goes wrong. This is what you get. So similarly, you'll get an email that goes to a mailing list and to you and says there is a build failure on this staging branch. And you'll get some details about the failure. So in this case, Qt has failed to compile for Symbian, S60 5.0. It tells you the test machine that was doing the test. It tells you the script that it was running. And then, if possible, it'll give you a nice snippet of the error message. So in this case, there's one line out of the compile failure error message pasted into this email. And then there's a link to a build log where you can see all the details. Okay, so this bit of detail about the compile error, there's no easy way to extract that for all tools. You might think that you could read standard error from tools. Unfortunately, it is quite common that tools do not correctly use standard out and standard error. So all of these compile errors are basically gathered by iterating through a huge list of regular expressions and figuring out what's interesting. And that's the kind of thing that is built into the system over time. So when the system was first put in place, there weren't many details at all. Now it's able to pick out lots of details. I believe we have a question over here.
Yeah. Do you get many false positives in the tests?
I'm going to talk a little bit about that later on. Basically, the answer is yes, and I'll go into details later. All right, so this is the other case where you've caused some tests to fail. So this is a similar kind of thing. You're told that there's an auto-test regression in your staging branch. And here we have listed every test that failed. So there's two separate things here. There's the concept of a test case fail. That means an entire test program crashed, or it hung, or it failed to output a valid XML test log. And then there's the concept of a test function fail, which means the test program did manage to run to completion, but some test function failed because a qverify or a qcompare, if you're familiar with qtestlib, some verification step failed. And on the right here, it's listing on which platforms it failed. Okay? All right, so I've talked about how the system works, but I also want to talk about some of the challenges we've encountered when developing this system. So the first thing, the biggest thing really, is instabilities in various parts of the system. So before I was working on this system, I was kind of living in this fantasy world where hardware and networks and so forth, they just work. But I'm telling you now that they don't always just work. Okay? So I've been quite surprised at the amount of effort it takes to keep these couple of hundred test machines working all the time. We do have problems sometimes, like network going down. Actually, a big issue that we regularly face is lack of reliability in the network link between our Brisbane office and our Oslo office. So if network falls down between those two locations, that can cause some test failures. Okay, we also have instabilities in third-party software. So basically, Qt is not the only software that has bugs, right? So there's two different things here. The first thing is that third-party software can also have bugs, and they can be unstable bugs. They can be bugs that only happen sometimes. So a concrete example of this is that we used to have some Solaris tests failing every now and again, and it turned out that the version of GNU Make we had on our Solaris machines, it would segfault once in 1,000 builds or so. Okay, so that kind of thing generates incorrect results, and it's quite a pain. The other thing that I mean by instability of third-party software is that sometimes we are testing on environments that are themselves subject to change. Okay, so we are testing for MIMO 6 Harmattan, for instance. Now that has a set of packages that we're testing Qt on top of, and that set of packages itself is subject to change every single day. So if we update our test environment every day, then we're potentially getting compile failures, test failures that have nothing to do with the code that we're testing. So that kind of thing can be quite challenging to deal with. Oh, and finally, our own software can be unstable as well. So I mean, that's obvious, that's what we're testing for. But certain types of bugs can kind of play havoc with the concept of our CI system. And I will give some details about that in one of the upcoming slides. And finally, we hit scaling issues sometimes. So a lot of the software that we're using, it seems to work really well when you just start off, you do a little bit of testing. Then when you try to scale it up to have 250 machines and thousands of tests per week, you find little issues that have been overlooked and need to be worked through. Okay, so I want to go into a bit more detail about the kind of problems that can cause the system to break. Okay, so consider this scenario where on the left we have someone who has written some bad commits, and let's say that they have caused QMake to crash sometimes. Let's say it's a memory corruption bug. Now, because of the nature of this memory corruption bug, it might be that the build actually is able to complete 50% of the time. But 50% of the time, it's failing. So if we happen to be unlucky, these bad commits may just happen to pass in the quality gate and then make it into the Qt mainline branch, such as Qt 4.7. Now, if that happens, then after that, every set of good commits has a 50% chance of being rejected because of this problem. So that really causes a lot of pain, and there's no silver bullet solution to this, I think. Basically, we just have to try to keep on top of these problems and fix them as soon as they arise to make sure the system keeps moving smoothly. Okay, so this situation, it has occurred a couple of times, but it's not that common. The next situation, this is very common. Unstable test failures. So basically what tends to happen is that a developer writes some feature, and then they write some auto test to test that feature. And when they run that auto test on their 8-core workstation with 3 gigahertz cores and 4 gig of RAM, and nothing else running in the background, it works just fine. But what they've done is they've put into their test some asynchronous action, followed by some delay, followed by some verification. And what that means, since they've done an asynchronous operation and they haven't correctly waited for it to complete, the test now depends on performance of the system it's running on and the system load. Okay? So the timing characteristics on the machine of the person writing the test may be very different from the timing characteristics on the machines running the tests. So unfortunately, this means it's pretty common that people write tests that sometimes pass and sometimes fail with no changes to the code under test. Okay, so ideally the solution here would also be to find it and fix it as soon as it happens. But in practice, this happens so frequently that our strategy at the moment is to just have a blacklist of tests. So these are tests that we know are low quality, and we still run them and we still record the results, but they don't have an impact on the positive or negative result returned by the system. Okay? And we are definitely looking for a better solution for these problems as well. All right, so I've gone over a few of the technical challenges that we have, but that's only one side of the story. There are also social challenges, right? So what can happen is that a developer submits something into the system, they get back an error report, and it's some weird error that looks totally unrelated to their code, and they say, there's no way I broke this. The system is doing something wrong. Okay, so that's kind of fair enough, because I have just spent several slides telling you that there can be reliability problems in the system. So it's fair enough maybe that they have doubts about what the system produces sometimes. And there's no simple solution to this problem either. Basically what we do is we try to handle all kinds of reliability problems very rapidly. So every single error report generated by the system is reviewed by someone who understands the system, and any problems are ironed out as soon as possible. So over time, that hopefully gives people more reason to trust the system. Something else that we can do, specifically to address the problem of difficult to understand error reports, is that sometimes we can add some helpful hints. Okay, so for example, Qt has this option to compile within a namespace, right? So all of Qt gets put into a C++ namespace. Now, that's something that frequently breaks because most people on their developer workstations, they don't test for it. But luckily, if you break that, the compile error that you get tends to follow quite a predictable pattern. So in this case, we can detect that this compile error is almost certainly specific to a Qt namespace build. So we can add a little hint into the failure email and tell the developer, hey, why don't you try configuring with Qt namespace when you try to reproduce this? So hopefully that saves a few hours of developer thinking, what the heck's going on? How do I reproduce this? Right. Another problem that we can have is when things are just breaking all the time. There's one bug and then it gets fixed, and then there's another bug that blocks integration, and there's a release upcoming and people are getting very unhappy. Okay, so once again, this is a social problem and there's no technical solution, but we can improve the situation by trying to keep the CI system working fast. So if people are getting error reports back very rapidly, then the blockage time is reduced, everything works a bit better. We can also manually adjust the priority of our tests. So let's say that the Qt WebKit branch was broken, the developer claims they've submitted a fix, but it's currently not scheduled to be tested again for another 10 hours. If none of the other staging branches have anything considered important in them, then we can adjust the priority of the branches and test the important one first. Of course, that doesn't work if everyone claims that their changes are equally important. And finally, in extreme cases, we might decide, well, this test was passing and it's now failing, but it's not important enough to block continued development. This might happen if it's only a very minor feature, or it's a new feature. So blocking regressions between Qt releases is a lot more important than blocking bugs that only affect new features. But of course, we should only resort to that in very extreme cases. Okay, so basically I have talked a bit about how the system works. Of course, there's a huge amount of detail that I didn't cover. But if you're interested, you can talk to me afterwards about that. Now I'd like to go on to what are we going to do next. So the biggest thing is contribution model, open governance. Okay, so our staging branch concept, it really doesn't work when combined with the desire we have for open governance and accepting changes to Qt from people all over the world. All right, so what we want to do is find something better than the staging branch concept, something that allows changes made by people within Nokia and outside of Nokia to be treated equally, and basically we want a more direct path between Qt contributors who don't work for Nokia and the continuous integration system. Okay, so it would be nice if we could have internal and external developers all using the same test system. Now, there are question marks against most of these bullet points because there are not concrete answers to any of these yet, except for this one. It's pretty clear that we should start to make these build and test results public. Okay, so there's a small amount of work that needs to be done to make that happen, such as we have the problem that we're testing Qt on platforms or on phones that Nokia has not released, in some cases on phones they haven't even announced. So we can't just put the build and test logs for those platforms out there for everyone to see. We would expose details about these unreleased devices. But those things will definitely be worked through, and we will make these things public. One nifty idea that I've heard recently is that we could have our merge requests. So the usual way to contribute changes to Qt, if you're not a Nokia employee, is to create a merge request on gitorius.org. Now what we could do is we could take those merge requests, test them, and then we could attach error reports as comments to the merge requests. So that's one idea that would hopefully increase the quality of the kind of contributions that we're getting and decrease the involvement of Nokia developers, remove them as a bottleneck, basically. Okay, so other things that we would like to improve. Performance. Performance is a big thing. We've struggled with that. The nasty thing about performance is that Qt is always growing, right? So that means that it takes an ongoing effort just to keep the performance of the continuous integration system constant. So this is a very challenging topic. Some ideas of what we can do. We could investigate using a compiler cache tool on Windows. So at the moment, we are using Ccache on our Unix platforms. This is a tool that basically intercepts calls to GCC. And if it looks like the source code hasn't changed since the last time you compiled something, it's just retrieved from cache rather than being compiled again. So we're doing that on Unix. It would be nice to do that on Windows as well. Something else is distributed compilation. Basically, this is where you compile on multiple machines in parallel instead of just compiling on one. So we are already using distributed compilation for most things, but we could squeeze a bit more out of it. There's a handful of situations in which we're not currently using distributed compilation, and we should work through those to improve the performance of the system. Okay, now what I think would be the most significant performance improvement that we could get would be if we enable ourselves to run our automated tests on multiple machines in parallel. Okay, so right now, when we're testing Qt, we build Qt, and that can be distributed across many machines. We're using distributed compiler tools. And then when we go to run the auto tests, we just run them one after the other on one test machine. Okay, so that's really not making good use of computing resources. So this would be really nifty, but it's still in very preliminary research stages getting this working. All right, other thing is platform coverage. So I haven't actually written anywhere within these slides what platforms we're currently testing on. But basically the rule is if it's fast and stable, then we test it. So Linux, Mac, Windows, we do compile testing and auto testing on those. Other platforms such as Maemo, Symbian, MeeGo, we do compile testing, but generally we don't run the auto tests in this system because it's a bit slow. I just want to clarify also that we do run the auto tests, just not in this system because it has to be fast. Okay, so as a concrete example, testing on Symbian phones. So if we want to run the Qt auto tests on an N97 Mini, for example, that works, but it's the kind of thing at the moment where we have to start it and then wait overnight to see what the results are. So it would be really nice if we could speed this up, and this again ties into parallelizing the running of auto tests. And then we could integrate this platform into our continuous integration system as well. And finally, for certain projects, such as MeGo, there already exists some test infrastructure. So we should not reinvent the wheel. We should rather try to reuse, ideally reuse both the computing resources and the test scripts for these platforms that have already been written. If that's not possible, then we can at least reuse the test scripts on our own computing infrastructure. So this is likely what we are going to attempt to do to improve our coverage with respect to MeGo, for instance. Okay, test coverage. So this is something that can always be improved. We have all kinds of tests for Qt, and many of them are just auto tests sitting in the Qt source tree. All of those are already in the quality gate, but then there are some tests that need a little bit of extra work to integrate them. Okay, so testing the binary compatibility of Qt, for instance, memory leak tests is an interesting thing. So on Linux, we can use the valgrind tool to do memory leak tests. We could spend some time integrating that into our quality gate. There's all kinds of static code checkers. There are commercial tools like Coverity, and then there are open source tools as well. There has been some work done already investigating integrating those into our system. And performance tests, this is a big one. Performance tests are not that difficult to run, but they are difficult to assess the results. Okay, so there is another talk going on about this today, after lunch, I believe. But basically, the problem with performance tests is that you can run a performance test, you can get some results, and then how can you really give a binary yes or no answer as to whether it's better or worse than the previous test, given that every platform has some inherent variability in the results that you'll get. Okay, and finally, we should just have a lot more auto tests as well. So the test coverage of Qt is not 100%, and we should keep working until we get there. Okay, and the final thing is product coverage. So this system was initially developed for the benefit of Qt. So Qt has a quality gate. Its platform coverage is okay. I'd like to make it better, but it's okay as it stands now. Qt Mobility, that also has a quality gate. So every change to Qt Mobility is regression tested. But that needs a bit more improvement in terms of platform coverage. Mobility is a bit of a different story than Qt, because Mobility has a lot more platform-specific code. Okay, so if you look at Qt, if you look at libqt core, for example, things like your container classes, they're the same code on every platform. Qt Mobility, on the other hand, almost every component in Qt Mobility has completely different implementations for Symbian, for Maemo, sometimes completely different implementations for different variants of those devices. So it's more important for mobility that we increase the platform coverage there. Qt Creator and the SDK currently does not have a quality gate. That's mainly just an issue of the time and effort and priority. It's not as important for Qt Creator because the team is smaller, and Qt Creator itself only targets the desktop platforms. Okay, and I would like for us to someday get to the point where we can offer this kind of service to any kind of research projects that our developers come up with. So things like Qt 3D and Lighthouse, both of those are technologies that are being discussed at this Developer Days. Right now, these do not have a quality gate, and it would be nice if we could provide that. Okay, so that's all the set content that I wanted to cover, and we can open up for questions now. Yep. Wait for the microphone.
I have a question on the developers. You said Qt is developed by 200 Nokia developers, and how they are distributed around the world. So what locations do you have?
I don't have any information about that. So that number that I came up with, about 200, that is based on looking at Git log, taking all of the email addresses, and then trying to pick which email addresses are duplicates. So that's why I said it's approximate. There's no way to give that information because when people sign up to Gitorious, for instance, we don't ask them to give us their country details. So.
You said you didn't integrate continuously with mobile platforms like Symbian. So is there any kind of management system for that, or do you just run it manually?
There is. So what I'm talking about here is only it's only one part of the automated testing that we do. Things like running auto tests on Symbian devices, that is done all the time. It's just not integrated with this accept or reject kind of mechanism. So yeah, we do have the infrastructure in place for that.
So it's not manual. You don't. The developers don't have to run manually. No. So what kind of management system do you use for that?
That is. Well, we have several systems, and some of them are integrated together. We have teams that use cruise control and Ant to do Symbian auto testing, and then we also have systems that contact cruise control and kick off a build, and then retrieve the results back. Over here.
If I got you right, you have this staging branching for your ongoing development work. And I just wonder if you have some kind of maintenance branches for the older stable versions of Qt, and how you integrate those maintenance works on older versions within the development branches.
Okay, so that's actually exactly the same process. So for Qt 4.6, for example, that is the oldest branch that still has any development. So Qt 4.5 has no development at the moment. Qt 4.6 has bug fixes only and critical bug fixes only. And that is using this system, staging branches and so forth. So there's no difference. The only difference is the amount of traffic that there tends to be in the staging branches. But at some point of time, we will decide that Qt 4.6 is not getting any changes anymore, and we'll just delete the staging branches.
I was wondering, wouldn't it be possible to somehow speed up the whole process by not testing everything for every change? I mean, I can imagine if you have changes in WebKit that it might not be necessary to rerun all the tests for the basic parts.
Yep. A lot of people ask that, and I think that in theory it's a good idea, but in practice it's extremely difficult to implement. Implementing that correctly is basically equivalent to implementing the perfect build system that knows how everything depends on each other. So I would like for us to do that, but I don't think it's going to be feasible anytime in the foreseeable future. Basically, we can guess, but our guesses will be wrong sometimes. Yep, over there.
Hey, so what do you do with the regression test results which the continuous integration system produces? Do you have some like statistical analysis on those results to see whether or not particular code parts are more like prone to breakage or regression?
Currently, what we do is we keep all of the test results for each staging branch until the next time that staging branch is tested, and then they're all wiped out and replaced. That's something that definitely needs to be improved, especially for for the reason that you said, but I'm also very interested in gathering more statistics about failing tests for the purpose of determining which tests are less stable than others. So at the moment, we don't have that much data retained. We're definitely going to improve that.
I have a question a bit about documentation. We are using Qt with Qt test lib together with Hudson server, and then we have some code coverage tools. But there is no very good documentation on the website or some how to do this. So we had to figure out a little bit, searching in the internet and how the tool chain is working. Do we have some guidelines about code coverage and test lib and how to use the test lib on some test cases or examples?
That's something that historically has not received much attention, because all of the tests in Qt, they've been viewed as things to be used within Qt and not really by other organizations. With 4.7, we've started to improve that a little bit, and we do have a goal to, well, all the test infrastructure that I've talked about today, we want to try to make that a lot more public as well, including the scripts themselves. So that will, in a way, act as the documentation for people who want to set up similar kinds of systems. Okay, any more questions?
How many people do you have involved for testing in relation to 200 developers? 10%, 20%, less?
It's more than that. That's actually a pretty difficult question, because not all of the testing takes place within Nokia, right? So Nokia actually does subcontracting of a lot of testing, and I don't know about the sizes of the teams. But I can say that basically we have two different test organizations, if you like. So there's one kind of group that is working on automated test infrastructure. That's the stuff that I've been talking about today. That's maybe 5 or 6 people in total within the Qt organization. And then there's people that are doing more kind of system testing, manual testing, and that's about 10 people within the Qt organization, and then subcontractors. I don't know how many, sorry.
Also, have you considered to run the same quality gate on the before merging the branches on the each individual branch which are in development? And if you not, then why?
Yes, that's also a common suggestion, and I would say that it's very likely that we will start doing that. Actually, for mobility, we're already doing that. But there's a bit of a problem with that, in that as soon as doing that greatly increases the amount of testing that we're doing, right? So instead of testing on one thing at a time, we're potentially testing on 10 things at a time. So that also means that there's a lot more error reports that need reviewing to ensure the system is reliable, for instance. That's the kind of main blocker from my point of view. I basically want to make the system a lot more reliable before we expand it and do more testing. Yep, one more question.
In terms of how you evaluate whether a test is successful, have you done anything in terms of just comparing text outputs, making sure that build logs from different builds are the same? Is that a better way to understand where might be the problem, or anything like that? Thanks.
There have been some. There's nothing. We're not doing anything regularly that works as you've suggested, but there have been research projects that that have kind of gone down that road. I'm not sure if Qt is really the really a suitable product for that kind of testing, at least on Linux, Windows, Mac, for instance. The build system is kind of predictable enough that I don't think we need to do that kind of testing. We do have something along those lines a bit for generating our packages that we release. So when we release a package, we do basic sanity checks, such as, does it look like every file that was supposed to be put in the package really was? And does it look like we accidentally put anything extra in the package, and so forth? So not exactly what you're talking about, but kind of similar. Okay, I think we're done here, so thanks for coming along.